We're talking in this unit about chemical bonds, and chemical bonds have to do with a spectrum. There's a spectrum between elements sharing electrons, elements taking or giving electrons, and then everything in between is covered. And that's what the spectrum here is for. So a chemical bond is an attraction that holds two atoms together, and it'll take energy to break this bond. If we played on these things, as we discussed, the PBS learning interactives, if a positive and negative, as in an ionic bonding situation, get together, they want to stay together, and it takes energy to pull them apart. They don't want to come apart. They like sticking together. Likewise, if you have two atoms being covalently bonded, it's the attraction to the electrons that are holding them together. They stay together because the electrons that they're quote unquote sharing are what's holding them together, and to pull them apart would be difficult. All right, so that is what we're talking about. We're talking about bonding. It can take the form of covalent or ionic. And the reason any of this happens, the reason the world goes around in chemistry, is because everything wants to be a Kardashian. Everything wants to be like a noble gas. And that means having a full and stable s&p orbital for a total of 8 valence electrons. And you can achieve this by stealing or giving away electrons, which is ionic, which we've discussed a fair amount already, or sharing electrons with other elements, which is covalent. So if everything wants to be like a Kardashian, remember valence electrons are the outermost electrons. So all of group 1 has 1, all of group 2 has 2, group 13 has 3, group 14 has 4. Remember all this? And so 8 valence electrons, the noble gases have 8, and so that's considered the octet rule, the highest achievement in atom existence, that you want to get those 8 electrons. So the octet rule states that you want those 8 maximum in your outermost energy level, your valence electrons. And remember, the D and the F don't partake in this because it's the energy level you're in -1 when you start filling those up, or -2 for the F. So they're not in the outermost energy level. So going back to Boo Boo Jeffries and Scorpionox, Boo Boo Jeffries, remember, is down on this corner with the elements that don't like to fight for electrons. Scorpionox is up in this corner for the elements that do like to fight for electrons. The closer they are to noble gases, the more they want to fight. They're just so close. These metals are better off going backwards to get to a noble gas, so losing electrons becomes a more stable pathway for them, and they don't really care much about electrons. So let's take a look at some of those metals. Right here's potassium. It has 19 electrons, that outermost electrons all by itself. When that disappears, then it has 18 electrons like argon, and it thinks it's stable, and it thinks it's like a noble gas, and it thinks it's like a Kardashian, and it's pleased with itself. So losing that electron is helpful to potassium. Magnesium is also a metal, same situation, 12 electrons here. By losing those two outermost, it now no longer has it now has the valence electrons of a noble gas. Losing those 2 electrons, were highly shielded by the electrons underneath from the nucleus anyway, wasn't that big a loss for magnesium. So now that it's stable, the nonmetals gain for the opposite reason. Or for the same reason, they still want to be a noble gas, but they go the opposite way. They gain. So fluorine with its 9 electrons wants one more to have 10, like neon, so it'll pick one up. Oxygen with its 8 electrons wants 2 more to be like neon, so it'll pick 2 up. All right, so difference in the electronegativity, how good a fighter they are, determines what this happens. If it's a big difference, then that's going to be an ionic compound. So metals and nonmetals, something low like Boo Boo Jeffries and something high like Scorpionox, that's ionic, where the electrons are just swiped away. If there's a small difference, meaning both are typically high in their number, in their fighting ability, then that would be covalent. So ionic is a hostile takeover. Atoms will lose or gain electrons. Again, you should have learned all this in the PBS bonding thing. Sodium, by losing that one, becomes like a noble gas. Chlorine, by gaining one, becomes a noble gas. So they have this relationship where Sodium loses it to chlorine, and now because they're oppositely charged, they stick together. Covalent bonding shares. There's what we call a bonding pair. There's two electrons being shared between two atoms. There's other electrons that we call lone pair that are not involved in the sharing, but anything involved in the sharing are bonding pair, and that's what makes them stable like noble gases. So when we use our electronegativity chart, this one right here, you would subtract the difference in the elements involved, and if it falls between 0 and zero point 0.4, we would call that nonpolar covalent, so really an equal sharing. If you have a difference between 0.5 and 1.6, that would be considered still covalent, still sharing, but the electrons don't spend as much time with one atom as they do another. They're Because there's a larger difference, they spend more time with one of the elements than the other, but it's still considered sharing because they do split the time a little bit. And then ionic is considered a hostile takeover, so the difference of 1.7. So just looking at some examples here, if you look at lithium, which is 1, and oxygen, which is 3.5, when lithium and oxygen get together, that's a difference of 2.5, and as a 2.5 difference, that would be considered ionic, right? Big difference over 1.7, so that's an ionic. The electron leaves lithium and goes to oxygen. If oxygen's bonding with nitrogen, now the difference is much smaller, 3 and 3.5, a difference of 0.5. So 0.5, that would be considered polar covalent. So basically a sharing of those electrons with a slight favoring to the bigger one, and the bigger number being oxygen. So the electrons spend a little more time with oxygen than they do nitrogen. Maybe 3 weekends a month instead of 1 weekend a month for nitrogen, but they otherwise split the weeks evenly. If we were looking at nonpolar, so something like hydrogen with carbon, okay? Difference of 0.4, so that's considered nonpolar. They share it more equally. Remember, you can share things different ways, right? You can share a pizza, you can share toys. These kids are quote unquote sharing this toy, but this kid has it more often than that kid. So therefore, this would be an example of polar, where this dinosaur spends more time with this kid than it does that kid. Nonpolar is when you share and share alike. Everything is equal. No one has more access to the electrons than any other atom. So they're sort of in the middle. And that nonpolar happens when you have, for example, if oxygen bonds with itself, oxygen gas that we breathe, that's what it is. There's no difference between the two oxygens. They're both 3.5. So the electrons that they're sharing are shared equally, and like that. Now, the other kind of thing, right, is metallic, all these metals. What about when they get together? Well, look at the differences in their numbers. They're all pretty close together, right? So, sort of what you might want to call covalent, but it's not covalent because remember, covalent involves the pulling, and this is more of legitimate, I don't care. So, metallic bonding just has its electrons floating around a bunch of ions, and the example I give is if you've ever been to a concert and they have some beach balls out, the beach balls, the people hit it, they knock it over, they wait for another one to come, they hit that one, and they don't really care to grab the beach ball and pull it down and sit with it. They don't need the beach balls. They just know another one will come soon enough, and if they want to hit that one, they can. And that's sort of how metals are treating their electrons in a metallic bond. Since nobody really cares to have it, they don't care if it leaves, they don't care if it comes. It's kind of nice when it's there, and when it's gone, it's gone. But that's what's holding all the metal together, is these electrons swimming around. So another example, if you don't go to concerts, maybe you've been to a water park, and with the floaties, you don't carry your floaty with you all day. They don't assign you a floaty as you walk in. There's plenty of floaties when you need one, and for the most part, you don't really care if you have one, so you don't need to carry it with you all the time. So those are the best examples I can come up with that. So some properties, these are just some things to remember for multiple choice tests, right? Metallic, they're good conductors of heat and electricity because the electrons can move so freely through there. So if you introduce electrons, remember we talked about John voltage. If you introduce electrons as electricity, they can kind of get passed through in this situation, like a bucket brigade, right? You put an electron here, one will pop out the other side, and that's how electricity conducts through metals. They have good strength, malleable, ductile, all right, delocalized electrons like we were just seeing. So properties of ionic compounds, they're solids because they're stuck together, that positive negative thing. They form what's called a crystal lattice. You should learn to associate the word lattice with ionic. And a lattice, just to get clear on that, a lattice is what happens here um, after they come together. After they come together, it's coming. There we go. Because they're now charged, right? There's a plus and minus. You can't hold them away from each other. And this is never going to happen with just two atoms involved. There's going to be lots of atoms involved. So when it happens with multiple atoms, they're all going to just line up and stick together, like a plus being attracted to the plus and a minus being attracted to the minus. So just imagine all the atoms of sodium and chlorine, right, coming together. So this is what we mean by a lattice. It's a long, three-dimensional, multi faceted structure where they're all kind of stuck together, and it goes on and on in all directions. So that's what we mean by um, ionic compounds form a lattice. They have a high melting point because they're stuck together. We'll talk about that. They conduct electricity because they have charged things. So if you dissolve them in water or you dissolve or melt them down, they can move electrons around. Covalent don't exist exclusively as solids. They're liquids and gases. We'll talk about why that is. They have lower melting points than ionic compounds typically, and they don't conduct electricity because their electrons are actually being used. They're tied up in that fighting, and they don't really have time to be passing other electrons through. Whereas ionic, since the electrons have already passed from one to another, they're sort of charged and make a nice medium for electrons to be traveling through. Only nonmetals involved with covalent, and here's some examples of that. So what it really boils down to, we talked about the formula unit and this lattice, right? So the lattice goes on in 3 dimensions for ionic compounds. The pluses and minuses keep sticking together. But the smallest repeating unit is what we call the formula unit. This is always a purple and a green, right? Purple, green, purple, green, purple, green, over and over and over and over again. So that is the smallest unit of an ionic compound when we call it a formula unit, because it's just the lowest ratio of everything going on in this lattice. Molecules, on the other hand, which is a covalent situation, they have a distinct beginning and end. They're not stuck to each other. So here is ethanol, drinking alcohol, and you have your hydrogens, you have your carbons, you have your oxygens, and they just have a distinct beginning and end. It doesn't go on forever. This one isn't necessarily stuck to that one. So they're more defined and less confined. The molecules are. All right. So the reason why one melts and the other one doesn't has to do with that. When you melt a solid that is a covalent compound like water, you're not taking the hydrogen away from the oxygen. You're not breaking that bond. You're just separating whatever space was between the molecules. Whereas when you melt an ionic compound, now you really do need to pull the pluses away from the minuses and get them more motion. And they're resisting that because they're stuck together. So it's because you're actually breaking the ionic bonds when you melt ionic compounds that it takes so much energy to do it. And it's because the compounds are staying together as molecules, as covalently bonded, that they don't require as much heat to be separated from each other. All right, so there you go, a brief summary of the kinds of bonding and the properties of those.